Hello students, today we are studying about nuclear and particle physics. Okay, so the nuclear and particle physics. So the some basic points about nuclear structure. First we have to study some basic points. Basic points about nuclear structure. Okay, first point, remember about the order of size of the nuclei. Order of size of nuclei. Nucleus is Fermi. The order of size of nucleus is Fermi, that is 10 raised to minus 50 meter. Okay, so the order of size of nucleus is Fermi, 10 raised to minus 15. Order of size of atom we know 1 angstrom, about 10 raised to minus 10 meter. Okay, so the atom size is 10 raised to 5 times more than that of nucleus. So the volume of atom is 10 raised to 15 times greater than nucleus. Volume of atom is 10 raised to 15 times greater than that of atom. Nucleus. Okay, so you should remember about the nucleus, order of size of nucleus as Fermi, and for an atom the size as 10 raised to minus 10 meter, that is 1 angstrom. Next thing you have to remember about the nuclear radius. Nuclear radius. Nuclear radius, that is R, is directly proportional to A raised to 1 by 3. So R is equal to R0 A raised to 1 by 3. So we know that R0 is equal to 1.2 to 1.4 FM. Okay, so in a representation of a nuclei, that is X is an element, Z is the atomic number, and A is the mass number. A denotes that is a number of neutrons plus protons. Mass number A is equal to mass number, that's equal to number of protons plus number of neutrons. Protons plus number of neutrons. Okay, you interested about these things? Okay, and we know that what is meant by isotope. Isotope is same set, different A. A is mass number. Isobar, same A, different Z. Isotone, same N, number of neutrons is same. So, and also isomers are there. Isomers are that same set and A but different energy levels. And also something we should know about mirror nuclei. For that Z and N should be interchange pairs are the mirror nuclei, that is O8 17 F970. So n is equal to 70 minus 8, 9. Here n is equal to 70 minus 9, it is 8. So here z is equal to 8, n is equal to 9. Here z is equal to 9, n is equal to 8. So z and n are interchange pairs, are mirror nuclei. Okay. Next we have to know about mass defect. Mass defect. So for that, mass defect, you should know about the formula first of all. That's mass defect delta M is equal to ZMP plus A minus Z, that's equal to N, number of neutrons, into Mn minus M, where M is the actual nuclear mass. M is the actual nuclear mass. It is subtracted from this ZMP plus A minus ZMN. Okay, so this is components mass minus the actual nuclear mass. So this will give you mass defect. There should be always some difference. So what is the thing behind that is nuclear binding energy. Nuclear binding energy. So we should know what is meant by nuclear binding energy. That is energy required to dissociate nucleus into its constituent nucleons. Okay. So some energy should be lost when it forms a nucleus. That energy should be required to dissociate the nucleus into its constituent nucleons. So the mass of its constituent nucleons and the actual nuclear mass will give you the mass defect, and mass defect into c square will give you binding energy delta m c square, that's equal to ZMP plus A minus ZMN minus M c square will give you the binding energy. This is the energy required to dissociate the nuclei into its constituent nucleons. So the graph, there is famous graph is there with A, and here it is binding energy by mass number. So there is a graph like this, and it is maximum for iron 56, and it is around 8.8 binding energy per nucleon. Okay, so these are the things about binding energy, and average binding energy per nucleon is 8 MeV. Maximum binding energy per nucleon for IN56, that is 8.89 MeV. Average binding energy per nucleon for average binding energy per nucleon, that is 8 MeV. For iron, that is 8.89 MeV. Nuclei with the alpha particle constitution have more binding energy per nucleon. Even nuclei are more stable. That is very important. Even nuclei are more stable. Even nuclei are more stable. Have here even means Z and Zn. Z or N Z or N or A. Okay, that are even, Z dot N or A. So odd out nuclei means odd out nuclei are less stable. So first you have to remember that even nuclei should be stable. Odd nuclei is less stable. So next you have to know about packing fraction. So packing fraction, it is an important thing. Packing fraction. So the packing fraction, which is defined as the mass defect per nucleon. Mass defect F is equal to delta M by nucleon, that is A. So delta M, we know that mass of its constituent atoms divide minus its nuclear mass. For a packing fraction of an element, we should minus by atomic number. Mass number. Mass minus mass number divided by A will give you the packing fraction. Okay, F is positive for very light and heavy nuclei, and they are not stable. Nuclei with N very greater than Z also very stable. N is very greater than Z, it is very stable. Next, we are studying about the nuclear properties. Nuclear properties, one thing, we know that size. We know the radius R is equal to R0 A raised to 1 by 3. So V is equal to directly proportional to A. From that we know that volume is equal to 4 by 3 pi R cube. From that V is directly proportional to mass number, we know that. So R cube means directly proportional to A. From that V is directly proportional to A. So the size of the nucleus R is equal to R0 raised to 1 by 3. R0 is equal to 1.2 Fermi. So distance of closest approach, that is we discussed in Rutherford experiment, in which alpha particles with the given kinetic energy come close to the nucleus, they feel a force of repulsion. At a certain distance, kinetic energy is equal to 0. After this, alpha particle turns back and kinetic energy starts increasing and potential energy starts decreasing. The distance of closest approach is D. So the kinetic energy is 0 and turns back, and kinetic energy starts and potential is decreasing. That distance, kinetic energy is equal to 0. That distance is 2z z bar E square 4 pi epsilon 0 mv square. Okay, so we can write like this: z bar E square divided by 4 pi epsilon 0 kinetic energy. So we equated with the kinetic energy with potential energy. So from that we get that expression, distance of closest approach. Z is the charge of alpha particle and Z dash is the charge of the nucleus. And we know that the density D is equal to mass by volume. Mass by volume, that is m divided by 4 by 3 pi r naught cube. That is, we know that m is the mass number, r naught cube, it is also proportional to mass number. So it should be a constant, that is 10 raised to 17 kilogram per meter cube. It is a constant. Nuclear density independent of the atomic mass A. Independent of the atomic mass A. Okay. So nuclear density, it is independent of mass number A. So this is all about nuclear properties, we need to discuss about mass defect, binding energy and separation energy. These three things are important for nuclear properties. Mass defect, we know that it is a measure of mass defect. It is a measure of binding energy of an atom. Measure of binding energy of atom, mass defect. Measure of binding energy. More the mass defect, more tightly the nucleons will be bound in the nucleus. Mass defect is more, delta M, mass defect is more tightly the nucleons will be bound. It should be more tight. That is, tight should be big. Mass defect is more. Mass defect generally increases as the number of nucleons in the nucleus increases. So mass defect increase with the number of nucleons, that is A only, that is increases with the delta M. Okay, delta M is increased with the number of nucleons in the nucleus increases. Packing fraction, we know the formula, F is equal to delta M divided by A. Delta M, mass defect divided by A, mass number. Smaller the values of packing fraction, more stable. F is very small, it is stable, and vice versa. Packing fraction is very big, they want to escape, that it is not stable. For light nuclei, hydrogen 1 2 and hydrogen 1 3, packing fraction is very large. It is very large. Hence, nucleons in this nuclei are loosely bound. Okay, packing fraction is very large. Hence, the nucleons in this, it is loosely bound. As mass number A increases, F goes on decrease. A increases, smaller value means it is stable. So F is very big means it want to escape. So here the nucleons are loosely bound in hydrogen 1 2, hydrogen 1 3. As a mass number A increases, F goes on decrease. For nucleon 16 to 180, F become negative. That is, atomic mass minus mass number, it should be a negative quantity. Mass number is bigger than atomic mass. So are strongly bound in the nucleus. Packing fraction is negative means it is strongly bound. Beyond A greater than 180, it is F is positive, and A greater than 235, that is unstable. So this is all about the packing fraction and all. Packing fraction is very less means it is stable. Okay, at very small packing fraction is big, at very big packing fraction is big. So at the two extreme conditions, they are behaves as an unstable. Okay, that is the all about conclusion about that. Next it is we have to understood about binding energy. For that, you should remember about the energy that keeps the nucleons together in a bound state. Binding energy means it helps to retain or to continue the state in a bound state. The binding energy keeps the nucleons together. So the binding energy formula, we know that the constituent nucleons mass minus M, the actual mass of nucleons, into C square. Actual mass of the nucleus into C square. So maximum binding energy per nucleon, that is equal to 8.89 MeV for iron 56. We know that average, that is 8. And next we have to know about separation energy. Okay, for separation energy we have to find SP, proton separation energy, neutron separation energy. These two things we have to know. We know that proton separation energy, if you are considering an element with the atomic number A, mass atomic number Z and mass number A, it is changes to some other element Y with the Z minus 1. One proton it emits one proton, that's Z minus 1 A plus 1 P11. Okay, so the proton now it is ejected from this. Okay, so for that SP is equal to the binding energy of the previous state minus binding energy of that new state, that is Z minus 1 A minus 1. It is also A minus 1 now. So SP, that is separation energy, proton separation energy, can be get from also the mass number My minus Mx plus Mp into C square. That is also get from this. Also the binding energy change will give you the separation energy. Similarly, we can get the separation energy, neutron separation energy. We are considering an element XZA changes to XZA minus 1. Atomic number is not changing here, N01. So separation energy means binding energy of previous XZA minus binding energy change will give you the separation energy of proton or neutron. And also the mass change, okay, mass change initial minus final into C square, that is also will give you the neutron separation energy. Okay, reactant minus products into C square. And magnetic moment, nuclear magneton mu n, that's equal to EH cross divided by 2mp. So we know that 5.058 into 10 raised to minus 27 joule per Tesla, and that is magnetic moment, nuclear magnetic moment. Mu p, that's equal to EH cross divided by 2mp into Gp. So Gp by 2 mu n. Mu n is equal to nuclear magnetic magneton, and mu n is equal to EH cross 2 by 2 mp into Gn. Okay, so EH cross by 2 mp, that is mu n, that's equal to 5.058 10 raised to minus 27 joule per Tesla. When we are considering mu p, Gp into mu n, Gp by 2 into mu n, and mu n is equal to Gn by 2 into mu n. Mu n is equal to EH cross divided by 2 mp. Okay.